Okay, welcome to your very last chapter. Welcome to the end of Bio 2. So with this, restoration ecology is near and dear to my heart. In the last chapter, I was talking about seagrass, and I mentioned that it's a keystone species. I had noted that I was doing seagrass restoration out in St. Petersburg. And it was just that. We were looking at more efficient ways to get the beds that were damaged to function like they were not damaged at all. Unfortunately, with a lot of these systems, really, the answer is don't damage it to begin with. But how reasonable is that? I mean, we are a species, we do what we do. Most species change the environment to benefit their needs. Humans are really no different than that. So, like I've been saying for several chapters, then we need to be cognizant of this. We need to understand what we're doing, what it means to the bigger picture, and therefore how to work with a system so we get what we need. We also still give the environment what it needs. We are still part of the environment, whether we want to admit it or not, and therefore if it's healthy, we're healthy, that kind of idea. So the ecosystem, I talked about it last time. It's just the environment and everything within it. So last chapter was community ecology. And therefore we were talking about that, what's found there, how do they interact, how do nutrients flow, how does energy flow, the trophic webs, how does, yes, feeding happen, but energy within that happen. Really nice that this author is reminding us about the microbial ecology, like bacteria. People often forget that. Microbial ecology is very important. Understanding like the organisms in soils and sediments and how they function is, again, very important. So we can have something very small up to the entire um, forest to work with. Aquariums are great. If they're done properly, they are a microcosm. We even call them mesocosms, where it's a small subset of the natural environment. And if you set it up properly, you can test in lab things that might be much more difficult to test in the natural environment. And even up to and including illegal. I read papers that were done in like the 50s and 60s that you would never get away with doing now. And granted, while the data was useful, very destructive, some of the projects that were done, which is why you can't do them anymore. So in that case, not that I'm advocating doing something destructive in a lab or hurtful in any way in a lab. I mean, bioethics are still very important, but it allows you to at least set up something, even hypothetically. So maybe you're modeling something. You're not even using an aquarium. You're just using mathematics and computer software to model. I think I noted that with global ecology, but you might choose that. So you can choose something like just having a fish in an aquarium and maybe you're feeding it and seeing how ecomorphology works, all the way up to computer programs where you're modeling, let's say a meteor strike and how, can something not just repair itself, but how long it might take to repair itself. You never get away with, well, let's simulate a meteor strike and have it destroy, 250 square kilometers of forest. That's just ridiculous. So you would not just use a mesocosm in that case, aquarium, but you would do something in a lab. That's maybe computer modeling. So there's a lot of ways to do this now. And global ecologists do use a lot of computers for it. So it's a way to study. How do you study the entire planet? That kind of idea. It's dynamics. It's really difficult. How do you deal with all the energy and the cycling of the chemicals? This gets into the biogeochemical cycles. How do you deal with that? So we have a phrase here in ecology, energy flows and nutrient cycle. And that's a great phrase to remember. So as ecologists, then we study this. Now, you've already had some work on this in Bio 1. In this book is chapter 8, basically dealing with thermodynamics. And so I mentioned in my Bio 1 how there's really 4 thermodynamic laws: the 0th law, first law, second law, third law. And now we focus a lot on the first law and second law. First law, law of conservation, mass energy. Second law, and even third law, dealing with things like entropy and when things become unavailable to a system. So there's entropy there, and how, positive and negative delta S. So we worry about that, how things are transformed. And when you go from being usable to non-usable energy, up to and including, say, things like heat death of the universe. And we can still talk about those things as well. So even ecologists can chime in on some of these discussions. How does this energy convert it from one thing to the next, since we don't think we lose energy, and it should be accountable. And then also, of course, that energy and matter are interconvertible. Einstein had a few things to say on that. So there is your law of conservation mass energy, that you can neither create nor destroy matter in the universe. It only changes in form. So we talk about that. If it goes from A to B to C and back again, how is it doing that? Like nutrients. How are they coming in? How are they getting out? That kind of idea. So we do talk about ecosystems being open systems. Energy flows in, energy flows out, mass comes in, mass goes out, that kind of idea. But remember, this is just an ecosystem. What about the entire planet? So you can ask that question. Is the Earth, it's still not letting me do this sometimes. Shoot. Well, poop. I don't know what it is. I think Teams is not playing nice today because it's only happening when I'm doing Teams. So I'll come back to this later. There's a red tide happening in Tampa. I'll probably just have to reference that. Let me get that out of the way. See if I can get back to this. Okay. So some script may be running. I don't know what it is. But anyways, so you can ask that question. Is Earth an open or closed system? Notice right here, this site is saying, nope, it's a closed system. At least in regards to matter, it's a closed system. This side is saying Earth is an open system, at least for energy, it's an open system. And then this one says Earth is mostly a closed system. So what is it? And that's coming from NASA. So, and that's because you have to ask the question, can anything enter or leave the Earth? Well, obviously energy can, but what about matter? Well, yeah, so things could obviously hit the Earth, everything from cosmic dust to meteors, asteroids. So meteorites and asteroids can come our way. And when something big hits us, can anything leave the Earth? Certainly things can. So I like how NASA states this. It's mostly a closed system. I think that's a better way to put it. Let me close that because I don't need that anymore. Can I get back to the lecture? There we go. Okay, sorry that my computer is being a little bit fussy. So again, we can ask it both on a smaller scale and a bigger scale. So we've already talked about this. Think about last chapter. We had the primary producers and primary consumers and secondary consumers, all the way to tertiary consumers, and finally the apex predator. This is just reminding you of that. It didn't talk about the detritivores, so decomposers, very important to recycle nutrients. I mentioned before in the class how bacteria and fungi are the primary decomposers on the planet. It just kind of is unfortunate when they're trying to recycle you before you're dead. You know, something like, I don't know, a athlete's foot or something like that. So yeah, deal with that, or ringworm, deal with that. But they are just doing their job. They're just trying to recycle nutrients. There's no like enmity involved or anything like that. They're not like out to get you. It's just kind of what they do because we need that. We need the recycling of nutrients, getting back to those biogeochemical cycles, and it helps to connect these feeding levels. So we still talk about the sun. Now, granted, there are places on the planet that have no direct connection to the sun, deep down in a cave, or maybe at the very bottom of the oceans, down in the abyssal zone, it's pitch dark, that kind of idea. But still, you can look at it this way. As the sun goes, we go. So it's not a bad way to look at things. And obviously, when the sun hiccups, this planet can hiccup. When the sun goes red giant, yeah, we're done. And then, of course, I don't think it's going to go supernovae. From what I've read, the thought is that it's going to go into like a dwarf system. But still, when it goes, we go. But right now, it really sets the budget on the planet. There's your primary producers harnessing all that energy. Look how big that arrow is, harnessing all that energy. And then goes to the primary consumers, secondary consumers, tertiary, apex, that kind of idea, and then it flows. So a lot of heat is lost. Now, thermodynamically, heat is a waste, but not so much biologically. Like we are both homeotherms and endotherms, so we generate and maintain body heat. We're losing it to the surroundings, but it is still useful to us. So I've actually got a little heater going right now. I have a Lynx Point Siamese who doesn't like cold weather. So even though it's not really chilly right now, it's 73 in Tampa. Yesterday was in the 50s, a poor little guy. So we had a heater going just for him. And he parked himself right in front of that heater, and he's been a happy camper all day long. So, man, our kids are pampered. So again, heat can be useful depending on the system, but thermodynamically, yeah, it's like an endpoint. And then, of course, chemical cycling flowing through the system. And there's your detritivores right there. So primary production is just that. It's the primary producers. They're setting budget to the system, and autotrophs obviously come up there. Again, there are places on the planet with no direct connection to the sun, so chemoautotrophs come by then. That might be down in like, I don't know, the hydrothermal vent communities, way down at the bottom of the ocean, where you have they're called black and white smokers, but all this like nutrient broth coming up, very hot water coming up. And so bacteria are harnessing that, and things come in and feed on the bacteria, then things come in and feed on the things that feed on the bacteria, that kind of idea. So they set budget in those systems. There you go, budget. That's a great way to look at it. They set it in that system. But overall, solar radiation really is the way it works. I mean, it really does set the system. And I still hold to that phrase, as the sun goes, we go. But even so, the sun, black body radiator, radiating out all this energy. Remember, plants only harness in the reds and the blues. So again, there's a lot of energy there that's kind of missed out. And yes, you could talk about chlorophyll A and chlorophyll B and the accessory pigments, that kind of idea, but the photosynthesizers are really very, very important. And not just plants, but algae, and there are some photosynthetic bacteria out there as well. So interesting little picture showing again productivity areas. I mean, this net primary product production right there, the rainforest areas. I mean, this is just very, very productive areas, very, very productive areas. Deserts, not so much. But one of the more intriguing things is look at the ocean. And it's not very productive, but the ocean is really important. It really sets budget because it's just so bloody massive. So it ends up being incredibly important. And of course, photosynthesis happens in the ocean, in the epipelagic, you get it there, certainly in tropical reef settings and coral reef settings that are photosynthetic corals. Obviously, you get some issues there as well, but it's just such a massive system, so it sets a lot of budget. So not just energy, but also nutrients, obviously very important here. And so with these nutrients, it depends on what nutrients are needed, but found in like lesser quantities that end up becoming the limited nutrients. Now, which one is limiting nutrient? Depends on the system. Is it going to be nitrogen? Is it going to be phosphorus? Is it going to be iron? It all depends on what it is, where you are, what the plants need. Nitrogen and phosphorus are the typical, there you go, are the common ones that set budget, but iron is not unusual. I don't remember if iron is on this this particular slide, but iron can be as well. This always reminds me of like going to, say, Home Depot or Lowe's, and you need to buy plant food. People often forget that, plants do need to be fed, and you need to get like the right fertilizer for that plant. So it often is like a nitrogen, phosphorus, iron ratio that you got to look at, especially nitrogen and phosphorus. What's the right ratio for this plant? What does it need for its nutrient loads? And then, to give it what it needs to grow properly. So again, we've studied that. We've gone to the oceans. Oh, there's iron. Yeah. So iron should be there somewhere. So we've gone to the oceans and we study these things, and we go to terrestrial environments and we study these things. And we find out, how to properly enrich soils if we ever have to need to. So eutrophication, we've seen that before, oligotrophic versus eutrophic. This is just an area that has too much nutrient in it. Now that could be natural, but also could be, runoff. That unfortunately I had to close it because something is not running right. And again, teams, something happening when I have teams running, so I'm not sure what's up. But there is currently a red tide outbreak in Florida. As of 3 days ago, I had heard it actually reached Tampa, and now we're looking at why. Is it a sewage runoff? There was some connection they were talking about it starting up after hurricane. I think it was Hurricane Ian, not so much with the tropical storm Nicole that went through. So maybe there was a backing up of nutrient issue, maybe some overflow from sewage areas, who knows? I'll have to go back and study this and find out why this extra nutrient is in the system, therefore why we're getting this red tide. And red tide is dangerous. It's not just dangerous for the fish and things that live in the system, it can be dangerous for humans as well. So read those warnings and understand what environment you're going into and keep yourself safe. Sometimes the government steps in, of course, and tries to help us out. It used to be there's a lot of runoff giving this nutrient into the system from things like washing machines. So don't quote me on this, but I want to say it was back in the 1990s that the United States went to this phosphate-free detergents to try to keep that nutrient out of getting into the lakes, rivers, and streams. And finally, the ocean. The ocean is always defined as being the lowest point. So lakes, rivers, streams under the ocean, and adding all that extra nutrient, which might lead to eutrophication, which might lead to like red tide events and things like that. So we're really trying to work on it, limiting bacterial growth. The cyanobacterial growth, remember, the red tide might be a dinoflagellate that's blooming from all the nutrients. And that itself might be toxic, but then you can't sustain that. At some point, the excess nutrient dies out, and so that begins to die. When that dies, the bacteria might start blooming and feeding on all this dying, like dinoflagellates, and then the bacteria might become toxic in its own regard. So it's like double hits that you're getting, where you get all these dead fish and other organisms. And again, it can hurt humans as well. So we got to be very careful with this. So we've already talked about this as well. Again, science, when you're talking about one thing, you're talking about something else. Remember, in terrestrial systems, temperature and moisture, so how much like rain and things like that are in the area really do set a lot of the scales that are going to be out there. So notice the primary production increases with moisture. That's right. We talked about even evapotranspiration last chapter. So again, how this precipitation is moving around. So again, in your terrestrial systems, precipitation and temperature for those climographs are really quite important. But I noted to you again that nutrient issues do vary depending on where you are. I've said several times already, and I think it comes up in this chapter later on as well. Tropical rainforests, there's so much moisture and so much humidity and so much there for heat. that there's still tons of decomposition. It just decomposes really fast, a lot of this material. So you lose a lot of soil nutrients, and the soils become depleted in the nutrients, and it's very hard for, especially damage when it happens for things to recolonize. So we need to know the system we're working with. What are the limiting nutrients, how to work with it, especially when damage happens, what kind of phosphorus might be there, and do we have to add it in? Do we have to add any of these in, that kind of idea. Well, secondary production then is not just the plants have to stop, but now somebody comes in and is going to at the plant. So here they have a caterpillar that's doing that. How much of the food that's coming in is actually going to be used to make new biomass? So we can look at that. We're not very efficient system, especially like mammals and things are really not very efficient system. That's what they're getting at. How efficient is it? So notice with the caterpillar, there were 200 joules that was bringing in as it's just like chomping away on that leaf, but only 33 joules of energy was actually used to make new stuff in it. It loses a ton of it in feces and cell respiration. So again, cell respiration is assimilated, so that's nice, but look how much you lost here, and it's not assimilated. Half of it is lost. Now, caterpillar, this going to be like a butterfly is much more efficient than mammals. I mean, look at this, birds and mammals, only 1 to 3% efficiency. This one is like approaching 50%. That's great compared to a mammal. So we're just not very efficient. Being homeotherms and endotherms, it takes a lot of energy to maintain that. And it's kind of an inverse proportion too. Like the smaller you are, the more you burn through fuel. So it's like my cats, if I eat all day long every day, if they could, of course, part of that is, are they entertained or not? Sounds kind of normal, right? But still, we're not a very efficient system. You can see fish better, but look at those insects. I mean, they're just much more efficient than things like mammals. So the efficiency is definitely there. This is called the rule of 10. But notice it really does vary, and it can be worse than 5%. It's really talking about when you go from one trophic level to the next, how much energy actually makes it there. And so how much is in the primary producers to the primary consumers or the secondary to the tertiary to the apex predator? By the time you get to the apex predator, there's just not much energy left over. So that tends to be a bit of a problem, which is where you get this pyramid, like a huge base of primary producers and then a teeny tiny tip at the top that would be the apex predator. And so when you look at these numbers, look at this, 1 million joules of sunlight came in. Only 10,000 joules is actually like simulated by the plants. That's only, what is that, 1% efficiency? That's not even 10%. Like I said, it could be lower than even 5%. So it's incredibly small. And then from the primary producers to the primary consumers, there's your 10% made it to that level. So at 1 million joules, only 1% here. Now at this level, you're 10% of 1%. At the secondary level, you're 10%, 10% of 1%. And at the apex predator, you're 10%, 10% of 1%. There's very little energy that makes it up to the tertiary consumer. And you know that when you look at like, I don't know, forest environment, what do you see more of? Plants or animals? Well, typically plants. And then of the animals, what do you see more of? Like insects or the mice? Well, typically insects. And what do you see more of? The hawks or the mice? You typically see more mice than hawks. That kind of idea. You go to savanna, same thing. What do you see more of? Plants or animals? Well, definitely plants. And what do you see more of? Herbivores or carnivores? Well, definitely herbivores. You see far more like Thompson's gazelles than you would lions. That kind of idea. Just very few up here because there's just such little energy. As a bit of a side note, we've noted with humans that it's not only healthier for you, it's healthier for the environment, feeding lower on the food chain. Now, that is not an argument to be a vegetarian. Remember, we're omnivores, but our diet is supposed to be heavy in fruits and veggies. So have you had any today? I haven't eaten much, but I have. So again, we need to be cognizant of this. And it's not only healthy for us, but there's just much more energy down here to deal with, making sure you get all the nutrients you need. So I had a little bit of protein today. I had some hummus, so some chickpeas. So again, you can still get it in different ways. I'm still actually feeding down here on the plants. And then I did have some crisps, and that's not sure that qualifies as food, but it's corn. So again, it's still down here. I didn't eat any animal at all. So again, you can still get the nutrients you need. Now, again, I'm not arguing for vegetarianism or anything like that. Just noting it's healthy to feed lower on the food chain, both for you and the environment, while still getting all the nutrients you need. We are omnivores. I'll leave the argument of vegetarianism to you. So these are two typical pyramids we see out there. This is a very typical terrestrial pyramid, a huge primary production base, and again, all the way up to apex predator, pretty small. Notice the marine environment or something like that, an aquatic ecosystem. You might say, wow, that's crazy that's such small primary producers and like zooplankton being a large one. But these are often not sustainable. So I've read again and again where these often crash. So be careful on these kind of inverted pyramids. All right, so that gets you to the biogeochemical cycles. And it means just that. It's such a great word for these things. Bio, obviously living things. Geo is just that, dealing with the earth. So geology and chemicals are chemicals. It's how these chemicals like nitrogen, there you go, nitrogen, phosphorus, sulfur, oxygen, carbon, whatever it is, even water cycles, how they're flowing from one thing to the next. It's really quite nice, including some of the less movable elements like phosphorus, like a rock, that kind of idea. That's usually where you find them. So again, how they move from one to the next. So we could talk about that, including sinks, which are like reservoirs of these things. There you go, so reservoirs. And notice they can still move. It might take a long time, where here we have maybe carbon and living organisms and plants and animals, and it dies and it gets pulled down and it becomes coal, which can get pulled down more, maybe made into rocks, that kind of idea. So now you can form sedimentary rock. Remember the rock cycle? I think we showed you that, but from igneous, sedimentary to metamorphic and back again. And it doesn't have to be that direct. There's a lot of different ways you can go through the rock cycle. So you can make rock, and then of course, weathering and erosion. So chemical and mechanical weathering can happen. You go back into soils and sediments, and they can go back into the system. So again, back and forth and back and forth and back and forth. And so as ecologists, we kind of pay attention to that. For these things, there's your water cycle. So water cycle, carbon, nitrogen, phosphorus, whatever it is. How are they moving? How are these things moving from one place to another? Why are they important? I had made a comment, especially in Bio 1, on this planet, where you find water, you find life, that kind of idea. And I still hold to that kind of comment. It's really quite important. So again, how is it important? How does it get from one place to another? Where are those reservoirs? That kind of idea, and how does it go back and forth between these two? So the water cycle, and first off, we have an unequal distribution of water. The northern hemisphere is considered the land hemisphere because most of the continents are in the northern hemisphere. The southern hemisphere is currently considered the water hemisphere. Most of the water is there. But when you look at the surface of the Earth, about 70 to 75% of the surface of the Earth is water. Again, it depends on the research you read as to exactly that number. But of that 70 to 75% being water, the surface of the Earth, the vast majority of that is marine, seawater. So for terrestrial organisms, that's not very good. You don't do this, please. Don't go down to like St. Pete Beach and dunk your head in the water and take a drink. You're not gonna like that very much. So you're only talking 1 to 3% being freshwater, and the vast majority of that right there is bound out in ice sheets and glaciers. And the last time I looked, there were not many ice sheets and glaciers in Tampa, Florida. So that means almost everything we do is off of groundwater. That means everything, cooking our food and washing our clothes and taking a shower and watering our lawn or whatever it is, which means we have very little water to work with. We can easily run out of water. And even a place like Florida probably has one of the highest, if not the highest amount of standing water on the planet, and we can still run out of water in Florida. Water is absolutely a precious resource. So we pay attention to that. How does it move from one thing to the next? So you can see the major movements here from an aquatic system, in this case, the ocean, to land and back again. I sometimes do get asked the question, does it rain over the ocean? It's a perfectly valid question. It's one that's directly answerable. Do we get storms over the ocean like a hurricane? So the answer is yes. So it's nice that the author is reminding us of that, not just that it rains, but it evaporates, sure. It certainly rains over land and it flows. Like I said a few minutes ago, it goes from higher point to the lowest point, and by definition, the ocean is the lowest point. You can get areas lower than that, but it's just by definition. And so it flows, lakes, rivers, streams, and even these aquifers. Aquifers are just water underground. Now, usually aquifers, you can have a semi-confined aquifer, a fully confined aquifer, that kind of idea. But they usually have recharge zones that come in. And you got to be careful, though. That looks like seawater to me. So you got to be careful that you don't take too much water out of an aquifer and get seawater to get into it. That's called poisoning the aquifer. And that could be problematic. So we need to be careful with these sort of things. And of course, over land, groundwater running off, that kind of idea. There's a lot of ways you can do it. There's evapotranspiration, a lot of ways water flows through the system. So it's good to be aware of that. The carbon cycle is pretty direct. I mean, obviously, we're exhaling carbon dioxide. I'm talking right now, so obviously I'm exhaling it. My cat, I'm sure, who is sound asleep, is exhaling carbon dioxide. He looks really comfortable. So a lot of animals are exhaling it. Plants are bringing it in, that kind of idea. The oceans, I just saw that word, is a great sink for carbon from the atmosphere. So there are a lot of ways it moves back and forth. And you can see that here, the major cycles, but really nice that Campbell reminds us all this burning is putting excess CO2 in the environment. I'll come back to that in a second. Now for animals and the fish down here and the decomposition, nobody argues against that. Please keep breathing, that kind of idea. And I just noted that the ocean is a great sink of carbon dioxide. So, these things happen. But when we're doing this, that becomes problematic because remember, when you put CO2 into an aquatic setting, it drops the pH. Think of like a soda. You have the carbon dioxide as a carbonated beverage. It drops the pH. So this can lead to the acidification of the ocean, which is immensely problematic. So we need to be, again, aware of these kind of things. But another thing I note is that people say, well, wait a minute, plants are taking in CO2, so the plants will save us. No, remember there's C3, C4, and CAN plants. Some plants do better with excess CO2, some plants do not. And even then, it seems like humans are doing their darndest to destroy plants and therefore like forests on the planet. I noted too, some research indicates there's only 200 years left of forest on Earth. So you can't look to this. We have to look to ourselves to stop this. Look for alternative sources. I teach environmental science, and the ecologists I know, the environmental scientists I know are not saying, like, let's go back and live in caves. No one's saying that, but they're saying look for alternatives. We need what we have. No one's arguing against getting rid of this technology and having a car. Although having more efficient cars would be great, having cars with no emissions would be great. But that's the point. Developing the technology to replace the current technology so we still have what we need and we're still giving the environment what we need. That's kind of where the trend is going, and it has been like that for a long time, at least with the scientists. Ah, yes, the nitrogen cycle. It's complex, particularly because of this one, diatomic nitrogen. Virtually nothing on the planet can access diatomic nitrogen except bacteria, but we need it. Right now, as you're breathing, as I'm breathing, I'm bringing in, of course, atmosphere, and I'm sure, as you know, 78% of our atmosphere is nitrogen. About 21% oxygen, and then we have our trace gases. But the nitrogen I'm bringing in is inert. I bring it in, I spit it right back out. I can't use it. You can't use it. But we need this. I mean, a lot of our macromolecules have nitrogen in them, so we need this for our nutrition, which means we have to look to something else to get nitrogen into the system. And that's going to be the nitrifying and denitrifying bacteria. To get the nitrifying bacteria, to get diatomic nitrogen into ammonia nitrates and nitrites, which you see here. And then the denitrifying bacteria to get the ammonia nitrates and nitrites back into diatomic nitrogen, which goes back into the denitrification, goes back into the atmosphere. And you can kind of see that here, both in an aquatic system. So even your aquarium has to do this. And of course, terrestrial system. There it is in the atmosphere. And so your nitrifying bacteria take diatomic nitrogen and get it into ammonias, nitrates, and nitrites. And then once it's in those forms, then things like, plants can uptake it. So a little bit of like an inlet here. So there's your diatomic nitrogen. And again, the nitrifying bacteria get into ammonia, nitrates, and nitrites. Plants can now uptake that. When plants uptake that, you come along and either eat the plant or you ate the thing that ate the plant, one of the two, and then you get nitrogen in you that way. And then you can make that into whatever macromolecule and things like that you need to. And then you have the denitrifying bacteria, which takes ammonia, nitrates, and nitrites and get it back into diatomic nitrogen. Absolutely critical, whether it's terrestrial or an aquatic setting. That includes aquariums as well. If you're ever going to get an aquarium, first off, I recommend start with freshwater aquarium. Don't jump right to seawater. It's too hard. And learn it well. Learn how to set it up and get it running, and then let it run for like 2 weeks and let all this set up, and then maybe put in some hardy fish and some hardy plants, and then don't do anything else. Just learn how to deal with that and clean it properly, and make sure you pick plants and animals that play nice with each other, because you need to establish the system. And bacteria is a critical part of the system. The phosphorus cycle. So I noted to you a few minutes ago, what are you going to do? The main source of phosphorus are rocks. So what are you going to do? Suck on a rock? Please don't suck on a rock. So again, we're kind of back into sort of this situation. We need to get it in a form that we can uptake. And then once we uptake it, we can make it into things we want. So there's your rocks. Chemical and mechanical weathering. It's going to get the rocks to eventually break down, and you get your soils and your sediments. And then once you have the soil and sediments, and plants uptake it. And then you come along and either at the plant or you at the thing that at the plant. And then you get the phosphorus in you. And now you can make that into whatever you need to. And you've been seeing this phosphorus since like Bio 1. I mean, it comes up all the time. And of course, it can go back into the system, sedimentation, and then of course back into the rock cycle again and again and again. So the cycling is important here. Understanding how the biogeochemical cycle works, how nutrients move. Remember the phrase, energy flows, nutrient cycle is important. And now they're talking about decomposition. So there it is, decomposition. And so we're right back to that subject that I mentioned several times over the last few chapters. We got to worry about that. So here's your tropical rainforest. And as I noted to you, it's so high humidity, so much moisture, high temperature. It's just tons of water moving through the system. So the soils are typically pretty pretty low in nutrients. And that's why there you go, low in nutrients. And that's why that damage up there is so critical. Now, as I said, even last chapter, that doesn't mean that if you have like a temperate rainforest, we'd be like, oh, willy-nilly, let's just go and knock everything down. No, of course not. We still need to be concerned about the damage that we do. But these things function. A temperate rainforest would function differently than a tropical rainforest. So again, as scientists, we just need to be cognizant of that, understand how the system works, and therefore work with it properly. So last but not least at all, finally, restoration. So we've damaged something. How do we get it back to functionality? Kind of the right answer here is don't damage it to begin with. But like I said, how realistic is that? So while we would love that to be the answer, maybe one day that will be the answer. Humans will progress enough where we live in perfect harmony with nature. I don't know. Someday maybe they'll find out. I'm sure you and I won't be able to see that. Unfortunately, I would love to be able to do so. But how right now, with the reality that exists, do we work with the system? And we're going to damage it. It just happens. So how do we at least get it back to some sort of functionality? So not just initiate, but there you go, speed up this damage that's done to get it back to somewhat functioning. And we could do it bioremediation or augmentation. So look at this. I mean, just look how much damage was done here. You can see there was something before it's and just like nothing left. So I mean, I can only guess what it was, maybe mining, something like that. And we need that. I mean, we all need mined materials. You do, I do, everybody does. So again, it happened and they got it back to some kind of functionality. It took 9 years, but now, even though it looks, pretty decent, is it? So you'd have to study it before damage and after damage. Is it really functioning like it did before? Maybe, maybe not. So that's where that idea, don't damage it to begin with, comes up. But how realistic is that? If this is a mine, and I do stress if, as I just said, you need mined materials, I need mined materials. Welcome to the reality that is as it currently stands. So that's where restoration ecology comes in. What can we do to mitigate the damage? Bioremediation is using living organisms to help deal with damage. It's really that simple. And I have one last video to show you that kind of typifies that. This is using fungus to deal with oil spills. So let me change over to the sound, and then you can hear the video.
So the other project that I've been doing for well over 10 years is neutralizing petroleum-based hydrocarbons using mushroom mycelium. And this is a project that we've done, that's been written up now in several journals. This is diesel, and this is mushroom mycelium. This diesel plug, the mushroom mycelium, is absorbing the diesel, it denatures it, and the mushroom mycelium produces these extracellular sweat beads, again, enzymes, lignin peroxidases. The lignin peroxidases break carbon hydrogen bonds, which is the bond that makes the primary bond in lignin. Well, that's also the primary bond in hydrocarbons. So they've been exquisitely well designed for breaking down a whole suite of hydrocarbon-based contaminants. And so we have now challenged a whole bunch of strains against a whole bunch of contaminants, and we found excellent results in breaking down PCBs, PCPs, dioxins, virtually all pesticides, most herbicides, all sorts of petroleum-based fuels, etc., diesel, gasoline, etc., etc. So the Department of Transportation in Bellingham, Washington, was being fined by the Department of Ecology, one state agency fining another state agency, treating it just like we would treat another individual or corporation. That's the way the law reads. Because they had a diesel contamination spill in a big transportation yard where all these buses were being stored. And because of toxic waste, the levels of these PAHs, which is polyaromatic hydrocarbons, was so high, this was off-limits facility. You couldn't do any activity there. So they invited 6 bioremediation companies, and so we had a little contest up in Bellingham, Washington, for who could break down this diesel contaminated soil the best. And so there were 6 piles that were created, and we had the enzyme chemical treatment people come in, we had the bacterial people come in, and we had other type of systems that were employed to break down these PAHs, these diesel compounds that are present in the soil. And so we inoculated our batch, and then we looked at the piles 4 weeks later. 4 weeks later, a group of scientists and government officials went up to Bellingham, Washington. They pulled apart the black tarps. The first tarp was pulled back, it was black and neutral, diesel-smelling soils, stinky, dirty black soil that was just stifling in its odor. Second pile, same story. Third pile, same story. Fourth pile, same story. The sixth pile, they pulled out, and ours was covered with oyster mushrooms. Okay, all right. And some of these oyster mushrooms were up to over 12 inches in diameter. So any of you collecting oyster mushrooms realize that, this is a testimonial to a happy mushroom. The fact that these mushrooms are so large. So we hit a home run. Now several other things happen. I knew I have to stop here in 5 minutes. I have 2 more slides. The mushrooms then, after about 6 weeks to 7 weeks, began to rot. The mushrooms produced spores. Flies were attracted. The flies laid eggs. Larvae began to be produced. Birds came in after the larvae. The birds brought in seeds. The seeds germinated. Plants and weeds started to grow. I don't have the final photograph, but after 8 to 10 weeks, our berm was an oasis of life, a green zone. And so we invited bacterial remediation because the mushrooms rotted. We invited phytoremediation because the birds brought in seeds. So I believe we found a keystone mechanism by which we can cause a domino effect of remediation that can break down toxic waste.
There you go. That is an example of bioremediation. Quite clever. And mushrooms are just amazing organisms. Fungi, just amazing organisms. And then augmentation, using organisms again to help get nutrients back in the system. So again, even in, what do you know, our state of Florida, there's a lot going on. So you might look at the watershed and how waters historically flowed. And then what happens, like the Everglades used to go not just from where it is now, like all the way up towards Orlando. That's how it used to be historically. And now it's just down towards, of course, Miami. So we look at these watersheds, and it's not saying like get rid of cities, get rid of Tampa, get rid of Orlando, get rid of this, get rid of that. No, we're talking about that. We're talking about how can we work with a system now to get it back towards a more functioning state. That's kind of where it's going. I was a little surprised that Campbell noted this newness of restoration ecology. From what I know, it's been around for a little while, but still, I like that that Campbell is highlighting this because it really is very important. Like giving the environment what it needs while still giving humans what we need as well. Well, there you go. You made it to your last slide. Congratulations. You are formally done with the course. So as always, if you have any questions, feel free to let me know. Beyond that, I hope you enjoyed it.